At precisely 1427 UTC on this date, ground stations at the European Space Operations Center in Darmstadt initiated continuous monitoring of the 3I Atlas probe as it approached perihelion, the point of closest solar approach in its elliptical orbit. This event marks the culmination of a 7-year mission designed to study solar coronal mass ejections and their interactions with interplanetary medium, with the probe now positioned at 0.17 astronomical units from the Sun's surface. The Atlas component, an array of wide-field telescopes integrated into the probe's payload, has been relaying high-resolution spectrographic data since launch, contributing to over 2,500 peer-reviewed analyses on heliophysics published by international consortia, including NASA and ESA affiliates. The mission's relevance extends beyond academic inquiry. It directly informs predictive models for space weather events that disrupt satellite communications and power grids on Earth. Detection methods employed here rely on a suite of instruments calibrated to withstand extreme conditions: cadmium telluride detectors for X-ray flux measurements, magnetometers for field vector mapping, and thermal radiometers tracking surface temperatures in real time. Telemetry streams, transmitted via the Deep Space Network's 70-meter antennas in Goldstone, California, and Madrid, Spain, confirm nominal operation up to this threshold, with signal latency averaging 8.4 minutes due to the probe's current distance. What can be confirmed at this stage is the probe's trajectory adherence to pre-launch simulations, with orbital parameters verified through Doppler ranging accurate to within 0.1 meters per second. Shielding protocols, consisting of multi-layer insulation and gold-coated Kapton films, have maintained internal temperatures below 85 degrees Celsius, despite external exposures nearing 1,200 degrees. Unclassified data packets reveal consistent particle flux readings aligning with ISOHO satellite baselines from similar passes in prior solar cycles. However, as the countdown progresses, the perimeter of our knowledge begins to contract. Telemetry indicates a subtle deviation in power output from the solar arrays, a 3.2% drop not accounted for in thermal expansion models. This irregularity emerges against a backdrop where all systems should perform within tolerances established during ground testing at the Jet Propulsion Laboratory. The mission's design incorporated redundancies for radiation hardening, drawing from heritage components used in the Parker Solar Probe, which endured comparable environments without such variances. Yet the data stream now shows intermittent spikes in electron density that exceed expected values by 15%. Challenging the assumptions of uniform solar wind distribution. These observations, cross-referenced with concurrent readings from the solar orbiter, suggest an anomaly in the probe's interaction with the heliosphere's edge, where magnetic reconnection events could be amplifying local effects. As the hours dwindle, the scientific community watches with measured precision, knowing that the next data burst will either affirm the mission's resilience or expose a flaw in our understanding of solar probe dynamics. This juncture represents not just a test of engineering, but the boundary where empirical evidence confronts the limits of predictive science. As the 3I Atlas probe advances deeper into the perihelion corridor, telemetry data from the onboard sensors begins to exhibit a deviation that defies the calibrated models established during pre-mission simulations. Specifically, at T-4 hours and 32 minutes, the magnetometers register a sudden oscillation in the local magnetic field strength, fluctuating between 0.05 and 0.12 microtesla over intervals of 15 to 20 seconds. This pattern contrasts sharply with the anticipated steady increase in field intensity predicted by the Parker spiral model, which accounts for the solar wind's radial expansion and should yield a monotonic rise without such rhythmic perturbations. Cross-verification with auxiliary instruments, including the electron spectrometer, confirms elevated particle energies correlating with these magnetic shifts, yet the thermal radiometers report no corresponding spike in heat flux that would explain the anomaly through conventional plasma interactions. This recorded deviation challenges the foundational assumptions of heliospheric physics as applied to close solar encounters. under standard conditions, derived from decades of observations by missions like Ulysses and the Solar and Heliospheric Observatory. The probe should encounter a uniform compression of magnetic lines as it nears the Sun, facilitating predictable data on coronal heating mechanisms. Instead, the irregularity suggests an localized instability, where the expected equilibrium between kinetic and magnetic pressures appears disrupted, potentially altering the probe's attitude control and data integrity. The anomaly is verifiable through redundant data streams. The primary X-band transmitter relays these readings with a checksum integrity of 99.8%, while backup Ka-band signals from the probe's secondary antenna corroborate the findings, ruling out transmission artifacts. Among the competing interpretations circulating within the mission's analysis teams, one posits an encounter with a previously undetected coronal loop fragment, a detached plasma structure ejected from the Sun's lower atmosphere during a minor flare event hours prior. This could induce the observed magnetic oscillations through reconnection processes, though it remains incomplete, as ground-based coronagraphs from the Mauna Loa Solar Observatory show no evidence of such ejections in the probe's trajectory path. A second explanation attributes the irregularity to instrumental resonance, where the probe's own structural vibrations, amplified by the intensifying solar gradient, interfere with sensor readings. This aligns with engineering tolerances, but fails to account for the synchronized spikes across multiple independent instruments, which were designed with damping mechanisms to mitigate such effects. A third, more speculative yet grounded in emerging theories, considers quantum scale fluctuations in the solar wind's turbulent regime, drawing from recent simulations using magnetohydrodynamic codes that predict intermittent bursts near perihelion. However, these models require field strengths an order of magnitude higher than observed, leaving a gap in quantitative reconciliation. The unresolved nature of these data points underscores a broader erosion in predictive confidence. While each interpretation draws from established principles, none fully encapsulates the anomaly's periodicity or its absence in historical datasets from analogous missions. Clarity diminishes as the probe's systems strain under escalating conditions, with preliminary algorithms struggling to filter signal from potential noise. Only through sustained monitoring in the ensuing hours, as the probe transmits its final bursts before a possible blackout, can the viability of these explanations be tested against incoming evidence, potentially reshaping our grasp of solar dynamics or exposing unforeseen vulnerabilities in deep space engineering. From the mission's inception, the sequence of observations has unfolded with the precision of orbital mechanics, each phase marking a progression toward the solar boundary where light and heat converge into a singular test of endurance. The probe's journey began with the initial insertion burn, propelling it into an elongated path that gradually tightened under gravitational influence, allowing early telemetry to capture baseline readings of the interplanetary medium, steady streams of protons and electrons flowing outward in predictable waves. These initial intervals established the rhythm, days of coasting through vast emptiness, punctuated by scheduled data relays that painted a picture of expanding silence, the sun's distant glow, a faint beacon against the black expanse. As the orbit contracted, the intervals shortened, compressing weeks into days, with sensors noting the first uptick in radiation, a subtle warmth infiltrating the probe's insulated core, signaling the approach to the heliosphere's turbulent layers. What has transpired thus far aligns with the mission blueprint. The probe has traversed the outer corona's fringes, relaying images of plasma tendrils stretching like silent rivers across immense distances, their scale dwarfing planetary systems yet invisible to unaided eyes on Earth. These observations matter because they bridge the gap between theoretical models and empirical reality. Each data point refines our maps of solar wind propagation, essential for safeguarding satellites that orbit closer to home, where even minor disruptions can cascade into widespread blackouts. Yet, as the timeline advances, imminent phases introduce constraints that heighten the stakes. the narrowing window for alignment corrections, where a single miscalculation could skew the trajectory, turning a controlled pass into an uncontrolled graze. Beyond the visible, gaps emerge, regions where the probe's instruments saturate under intensifying glare, leaving blind spots in the data stream. Pockets of uncertainty where magnetic fields might twist unseen, their silence a void that echoes with potential failure. The environment deepens this progression, the probe enveloped in a growing haze of ionized particles that scatter light into diffuse halos, distances collapsing as the sun swells from a point to an overwhelming disk, its surface a roiling sea of convection cells, vast enough to engulf worlds. The scale imposes a quiet immensity, the probe a solitary speck adrift in this luminous ocean, its signals traveling across light minutes of emptiness to reach antennas straining against atmospheric interference. As the countdown proceeds, the rhythm accelerates. Hourly checks yield to minute-by-minute updates, the probe's velocity mounting as gravity pulls it inward, each passing kilometer eroding the buffer against thermal extremes. The air in mission control thickens with this compression, operators monitoring screens where graphs climb steeper, curves bending toward thresholds where materials yield and electronics falter. Approaching the core milestone, the intervals tighten further, the probe's path now a razor edge between revelation and loss, with the next signal burst poised to transmit amid escalating interference, a fragile thread of information that could confirm resilience or reveal fracture. In this narrowing funnel, the unseen looms larger, what lies just beyond the sensor horizon, where plasma densities peak and fields compress into knots of energy, defying remote prediction. The sequence builds inexorably, each stage layering consequence upon the last, until the boundary nears, promising either the clarity of survival or the abrupt break of silence. In the hours following the anomaly's detection, the flow of information from Mission Control underwent a marked adjustment, with initial telemetry releases curtailed to essential metrics only, pending cross-verification by interagency panels. Statements from the European Space Agency and collaborating bodies, typically issued in real time during nominal operations, now emerged with delays averaging 45 minutes, reflecting protocols activated for data integrity review amid potential classification concerns. Conflicting analyses surfaced in internal briefings, where one faction attributed the magnetic oscillations to external solar influences, while another highlighted internal sensor drift, each backed by partial simulations but neither achieving consensus due to incomplete datasets from the probe's strained transmission bandwidth. This shift in dissemination protocols introduced layers of measured caution, as public updates limited disclosure to confirm trajectory adherence and system status, omitting details of the irregularity to prevent misinterpretation in broader scientific communities. The consequences of this uncertainty extended into operational domains. Mission teams deferred attitude correction maneuvers, adhering to restraint guidelines that prioritize avoidance of actions based on unvalidated readings, thereby extending the probe's exposure to escalating solar conditions. Scientific disagreement deepened as preliminary models failed to reconcile the data, with heliophysicists from the Jet Propulsion Laboratory advocating for enhanced particle interaction theories, contrasted by engineers at Darmstadt emphasizing hardware limitations, resulting in a stasis where no final interpretation could be endorsed without additional evidence. As the timeline compressed toward the perihelion apex, indications accumulated through fragmented signals, power fluctuations intensified by 7.4%, correlating with magnetic peaks, while spectral readings deviated further from baselines, narrowing the window for corrective interventions to mere minutes. Procedural reviews accelerated, yet retained their systematic pace, cross-referencing with archived data from prior missions to isolate variables, though gaps in historical parallels only amplified the restraint. The rhythm of monitoring tightened, with data bursts arriving at irregular intervals, each scrutinized for patterns that might clarify the anomaly's source, building toward an anticipated pivotal relay. At T-minus 1 hour and 18 minutes, the probe's final coherent telemetry packet revealed a structural realignment in the magnetic field configuration, indicating an induced plasma sheath enveloping the craft, inconsistent with all prior solar encounter models and suggesting an adaptive response within the heliosphere itself. The transmission ceased thereafter, leaving the dataset open to re-evaluation without closure. In the wake of the probe's transmission cessation, the confirmed elements of the event coalesce into a restrained chronicle. The Three-Eye Atlas craft adhered to its projected trajectory until the anomaly manifested, delivering verifiable data on magnetic field oscillations and plasma interactions that align partially with established heliospheric models. The induced sheath formation, captured in the final packet, stands as an empirical marker, its parameters cross-checked against redundant sensor logs and corroborated by distant observatories monitoring solar output. Yet much lingers in the speculative realm. The origin of the deviation, whether rooted in an unforeseen solar mechanism or an intrinsic probe response, resists definitive assignment, with interpretations fragmenting across disciplinary lines without converging on a singular explanation. This division underscores the limits of remote observation, where distance imposes a veil over direct causation, leaving the event's full anatomy to inference rather than autopsy. The broader implications extend quietly into the fabric of scientific inquiry, prompting a re-evaluation of how we model the sun's influence on engineered systems traversing its domain. What began as a mission to map coronal dynamics now illuminates vulnerabilities in our predictive frameworks, suggesting that the heliosphere may harbor adaptive qualities akin to those observed in terrestrial atmospheres, where equilibrium yields to emergent patterns under stress. For collective understanding, this serves as a measured reminder that discovery often arrives not through triumph, but through the friction of anomaly against expectation, reshaping protocols for future deep space endeavors and fostering interdisciplinary caution in data interpretation. Institutions, bound by procedural rigor, have initiated archival integrations of the telemetry into global databases, ensuring its availability for iterative analysis without presuming immediate breakthroughs. Anticipated steps involved sustained monitoring of analogous missions already in orbit, where refined algorithms will parse historical parallels for subtle precursors, alongside ground-based simulations to replicate the sheath conditions under controlled variables. Verification may emerge from incremental advancements in sensor technology, allowing probes to probe deeper with enhanced resilience, though such progress unfolds through methodical iterations rather than leaps. In this continuum, the event endures as a point of inflection, where the silence following the signal's end invites not conclusion, but ongoing vigilance, a testament to the inexhaustible dialogue between human ingenuity and the solar system's unyielding expanse.